We're going to look at an overview of what we're going to study in chapter 16. And along with that, I'm going to go ahead and cover 16.2 part 2. So just as a quick review, two of the new types of integrals that you learned last chapter were line integrals with respect to arc length, either for a function of 2 or 3 variables, with a curve given parametrically by this vector function. And then we also learned surface integrals for a function of 3 variables over a surface given by z is a function of x and y, and actually we looked at the other orientations as well. And the way that we accomplished these was to put them in terms of t. So we put any x's and y's and z's in terms of t given by the parameterization, and the ds part here, the ds was given by ds was the magnitude of r prime of t, dt. And we talked about some of the uses of those, some of the applications. For the surface integrals, the way that we did these problems is that we turn this into a double integral for f of x and y, and for z, we would replace the surface and the ds was related to the surface gx squared plus gy squared plus 1 dA. And of course we looked at all the different orientations depending on which variable was the dependent variable. Okay. What we're going to do now is combine these two ideas with the topic of the last section. We're going to look at these. We're going to look at applications of these. We're going to look at a vector field. We're going to find out in 16.2 part 2 that an application of a line integral in a vector field is a physical idea called work, which you have probably studied a little bit of, both in 5A and physics. And then an application to surface integrals, we're going to talk about in 16.7 part 2, and that idea is called flux, which you may have come across in physics. Okay? This whole chapter really is about these two topics. We're going to learn about work, and then we're going to learn a lot of different theorems and ways of computing this topic. And then we're going to learn about flux and learn about ways to compute with that. My advice to you on this chapter is to keep kind of organizing your thought in notes. See the big picture of this chapter, because we're going to be getting a lot of information, but it all boils down to applications of line integrals called work and applications of surface integrals called flux. And then the different ways of handling these computations. A quick review of what you should have learned back in Math 5A about work. If you haven't, this should give you enough to go on. But when a force acts upon an object causing a displacement of the object, it is said that work was done on the object. The simplest case is if you have a constant force applied in the direction of motion. So if I have some object here that I want to lift a certain distance, some distance d, and this object has a certain weight, let's call that F, maybe it's 3 pounds or maybe it's 5 newtons, so we have some sort of weight here. I'm going to move it a certain distance. Then if it's a constant force, the work just equals the force times the distance. The units here are typically either feet and pounds, which gives me foot-pounds, or newtons and meters, which gives me newton meters, also known as joules. In calculus, you should have learned that if we take a more complicated problem and instead we have this object that, let's say, we're trying to lift a certain distance, but this time the force is variable. Think about it. Maybe there's water in here and it's leaking out. So as I lift it, it's getting lighter. So that force is changing. So we have a variable force. In order to figure out the work done in that case, so many times in calculus, here's what we do. We don't know how to do this variable force. We do if it's constant. So that's when we go and we partition this distance that we want to move it, and we look at what happens on a small subinterval there. And even in that small subinterval, the force is variable. It's not constant. But what we do is we say, okay, well, even though it's not constant, let's assume that it's constant just on that little piece. We take that and we multiply by the distance. And we do that for each of those little pieces. We do it here and so on, and we add those up. Now that's where, in calculus, we got this idea here. What if we have a situation where we want to move this object in this direction, a distance of d? In fact, I'll call this vector d, and little d, this distance, would be the magnitude of that vector. And suppose the force doesn't go in the direction of motion, but is at some angle to the direction that we want to go. So this is my force. So if I want to compute the work done, what I have to do is figure out what is the component of force that is in the direction of motion. You know, we can always break down a force into this component and the one orthogonal to it. I'm just going to draw this in lightly. That's not really the one I want. In this case, the component of this force in the direction of motion, I'm going to call that F sub x. So F sub x would be the x component in that force. And so the work done is going to equal F sub x times the magnitude of d. Now, using my trig over here on this right triangle, F sub x over the magnitude of f would be the cosine of theta. So F sub x equals the magnitude of f cosine theta. So if I put that in over here, then work equals magnitude of f cosine theta times magnitude of d. That is, work equals magnitude of f, magnitude of d, cosine theta. Now this sort of expression, magnitude, magnitude, magnitude f, magnitude d, cosine of the angle in between, we have another way of expressing that. That is the dot product. So the work, when we have a constant force not in the direction of motion, the work done is F dot d. All right, so just as we did here, where we went from constant force in the direction of motion to variable force in the direction of motion, here we considered constant force not in the direction of motion. Now we're going to consider variable force not in the direction of motion. So again, I have some sort of object. I would like to move it this way, but I have some sort of variable force. So by variable force, this force is some function of what? X, Y, X and Y. It's moving in 2 dimensions this time. So this is going to be some function. This force is a vector, but it's going to be a function of X and Y. Let me show you what I mean in this picture here. Suppose that we have a vector field. It's a continuous vector field. It could be some sort of force field or gravitational field. And suppose we're trying to move an object along this curve right here. Okay, so we're trying to move the object this way. And we want to know the work done in moving an object, the work done by the vector field, the force field, and moving the object from here to here. Well, that's a variable field. The force here is different than the force here, is different than the force here. So that's variable. The force as we move this object is variable. So if it's variable, how are we going to compute the work? Well, similar to what we did here is we're going to partition this. We're going to break it up into little pieces. The work changes along that piece. Even within a subinterval, the work is variable there. But as we've seen before, if we look at a particular subinterval, let me suppose this was my subinterval here. The force is even varying on that subinterval, but it's such a small subinterval that we could treat the force as if it's constant on that subinterval. So if I were to take this part right here and blow it up, what I'm saying is we have this little piece, like so. The force is varying there, but this one force that acts right there, I'm going to draw that one. And now at this point, I'm going to consider what's going on here, similar to what we did in the constant force situation. We'll do that on each subinterval and sum them up. Okay? So that's the general idea. Let's put in a few more of the details. All right, so this curve is given by r of t, where t goes from a to b. So we'll partition AB into n subintervals of equal, it's not equal length, it's equal delta t, whether that's time or whatever the parameter is. So we'd maybe call this t0 and this one t1. Maybe t2 is way over here, t2, so that these aren't necessarily the same widths. We saw that when we were doing line integrals in the first place. We'll call this the width of interval 1 and the width of interval 2 and so on. So somewhere up here we have our ti minus 1 to ti. That will be our typical subinterval. So we will consider the ith subinterval, which goes from t sub I minus 1 to t sub I, and it has length of delta s sub I. as we've done time and time again, we will let ti star be an arbitrary value in that ith subinterval, and let's let, I'll call it pi star, which is x of ti star, y of ti star, be an arbitrary point in that ith subinterval. So let me just, I'm going to blow this up here in a minute, but let's just say, you know, pi star, arbitrary point there. Now, as I said, the force varies on the subinterval, but what we'll do is we'll find the force at this given point. So we'll put this given point into our force function here, and we'll find the force at that point. So the force, let f of, let me write it this way, x of ti star, y of ti star, be the force at the point pi star. This pi star, this point, is not the same as the p here. That's poor notation on my part. Okay, so it's the force at this arbitrary point. All right, so what I want to do then is figure out what is the work approximate work and I'll call that W, delta W sub I on the ith subinterval. So we're going to find the work done in moving the object here. Once we have that, then we'll sum the same thing up for all, take a limit, and get an integral. So how am I going to get the work on that subinterval? That's the key. So what we're going to do is we're going to use the idea that we talked about here. So this is where I'm going to take this piece, best as I can, and blow it up. So what do we have? We have from this point here to this point here, this is that length of delta Si. We have our point here somewhere, our pi star. This is our F at that point. Let me just write F for right now. This is our F. So what did we learn up here? That the work done in a situation like this is F dot D. So for us, that's going to be F dotted with this vector right here. So what is that vector? This point right here was P sub I minus 1. This point right here is P sub I. So the work here, delta W sub I, is going to be F dotted with Pi minus 1 to Pi. Now, another way of writing this is a vector from Pi minus 1 to Pi. I really want to kind of generalize that a little bit. I don't want to have to actually find each of those points and then find the vector for each subinterval here. So I want to generalize this. And so this is going to be equal to F dotted with T of Ti star times delta S I. Let's think about that for a minute. Here's what I'm saying. I need to form a vector from here to here. I don't really want it as a function of these 2 points. My variable that I'm partitioning is t. So I'd actually like to get it in terms of t and in terms of that delta t somehow. So if I want to form a vector from here to here, I know what the length should be. The direction, what is the direction? The direction would be if I were to find a unit tangent there. So this is at ti star. If I were to find the unit tangent, that's what this is. With a capital T, remember, it's been a while, but that was the unit tangent. So if we take this unit tangent and we multiply by delta s, that gives us a vector in the direction of u that has length delta s. So that will be the same as pi minus 1 to pi. And how does that help us get this into some sort of usable form? Well, I can rewrite, using the properties of dot product, I can rewrite that as f dot t at ti star. Take that dot product first and then delta si. And so that is the work done in moving the object this far. If we want the work over the whole curve, so again, I guess I should be a little more clear here. That's the work on the I subinterval. We sum these up over the whole curve and take a limit. Okay, so we're going to sum this up. Well, I equals 1 to n. We made n subintervals. And we'll do f. Let me just leave the variables out for just a second. F dot t times delta si. And we're going to take the limit as n goes to infinity. Now if we do that, f dot t, this is a vector field. This is going to be a function of x and y as well. If I take this dot product here, I'm going to get a scalar function. In fact, f is a function of x and y, but x and y on this curve are each functions of t. And this is a function also of t. This is going to end up being some function of t. So if I have some function of t here times delta si, this is a line integral. This is a regular line integral with respect to arc length. This is the line integral of f dot t, once I've taken that dot product, that is a scalar function, times delta si. So this is how we compute work of a force field in moving an object along a curve. Okay, so if we want to compute work, it's just a line integral, but instead of f of x and y here, we have to take a dot product to find out what our integrand is. That's all. Just as a reminder, if we're doing a line integral with respect to arc length, the way that we do it is we put all this in terms of t, and we do that using the parameterization of our curve. And then this ds part is that square root of dx dt squared plus dy dt squared, which is the same as magnitude of r prime of t. So in order to do this, I need to know what f dot t is. F dot t is my integrand. So let's work on f dot t first. So f f equals x, y, and 2x minus y. Now, once I find f dot t, that gives me my function here. I'm going to have to put that in terms of t. So I'm going to go ahead and put this in terms of t here. My x is t, and my y is t squared. So f, if I put that in terms of t, put in the t's, is going to be x times y, which is t times t squared, and then 2x, so that's 2t minus y minus t squared. So what do I have? T cubed and 2t minus t squared. Okay, that's f. I also need t. Okay, what was t again? T is the unit tangent. So we found tangent before by taking r prime, and we turned it into a unit tangent by taking the magnitude of r prime. So in our situation here, r prime is 1 to t. The magnitude of that is radical 1 plus 4t squared. So f dot t is the dot product here and here. Now when we take that dot product, we can leave that scalar function factored out and do the dot part first if we like, using the properties of dot products. So I'm going to leave that out there. That's going to be 1 plus 4t squared. And then taking the dot product of the vector part, I get 1 times t cubed plus 2t times 2t minus t squared. So that's 2t times 2t and 2t times t squared. Okay, so I just took the dot product here. T cubed, 4t squared minus 2t cubed. And that will then be 1 plus 4t squared and 4t squared minus t cubed. So that is this part. That's the f part. I'm also going to need the ds part. The ds part of a line integral is magnitude of r prime. So ds is magnitude of r prime of t. Or maybe you didn't use that formula, you used the dx dt squared plus dy dt squared. Either way, we would end up with magnitude here, 1 plus 4t squared. So the work just rewriting the formula there, is the f dot t, which I have computed there in green, times the ds, and we put this all in terms of t. So f dot t is 1 over 1 plus 4t squared times 4t squared minus t cubed. And then the ds is radical 1 plus 4t squared dt. And I need to have that here actually. There should be a dt here. And here. Once we've got it all in terms of t, then we use t's limits, and t goes from 0 to 1. So we just integrate this, and it looks kind of bad until we see that those two divided out, and we get 0 to 1 of 4t squared minus t cubed. dt. Which is 4/3 t cubed minus t to the 4th over 4, 0 to 1, which is 4/3 minus 1/4, which is 13 over 12. We'll talk more about getting a feel for what that means physically in just a minute. But point of this all is that here is an application for our line integrals. If our scalar function that we're integrating happens to result from the dot product of a vector field and a unit tangent, then that has a physical application called work. And to compute this, all we have to do, it's just what you already know how to do. You already know how to do this. It's just the first step is, what is our integrand? Well, we would have to take f dot t, compute f and compute t, put it all in terms of t, take that dot product. Now, you might have noticed something. You might have noticed, maybe, I don't know where you maybe noticed it, right here when I was doing t, I had the r prime of t magnitude. Right here, r prime of t, that magnitude. But then it also occurs here in the ds. And so in the t, you're going to get a 1 over r prime. In the ds, you're going to get an r prime. Those two are going to cancel out every time. And so what that means is that what's left here, let me write it. So this would lead me to f dotted with t. T is r prime over magnitude of r prime. ds is magnitude of r prime dt, and so those two are going to divide out every time, and so what we're left with is f dot r prime dt, f dot r prime dt. And once t is the limits there, then we need t's limits here. We don't put it over c anymore. Once this becomes a dt, this is not a line integral anymore. It has now become a regular integral of a scalar function. So this is a shortcut. For computing work. We don't have to find f and t and ds each time only to find out that that magnitude of r prime is going to divide out. We can jump straight to what we know to be left. So this is a shortcut formula for finding work. So work, here. This is the shortcut. This is what we're going to use to do the computation. This is what we're going to use for, let me call it, it's a shortcut for direct computation. This is what we're going to use. We're not going to go through all that trouble of finding those things that divide out anyway. Now, this is the way we define work, and I like to make sure that you understand that. In fact, normally, anytime I'm asked a question about work, I will write this before I write this. Because what happens is we get so good at going straight to the shortcut, but notice this is not a line integral. We've already gotten past the part where it's a line integral when things divided out. So it's easy to lose sight that the concept of work really comes from a line integral, that it really is an application of a line integral. So I like to write it this way and then write it this way and actually compute it this way. This is your book shorthand. dimension is up here too. It's your book shorthand. I don't really care for the shorthand because it doesn't really tell you how to go about computing it, and it doesn't really tell you what it physically means, but I do sometimes use that shorthand just because it's shorter to write. All right, let's go to the next page and look at another example, and then we'll come back and talk about this. So in this problem, we're being asked to find the work done by this vector field. So now we've got a three-dimensional vector field on a particle that moves along the line segment from here to here and then here to here. Okay, so this has a couple new pieces in it. First of all, let's call this A and then B, and then from B to C. So we have some sort of curve that is piecewise smooth, A to B, and then B to C. I'm not drawing those in the right placement or anything like that. I just wanted a visual here. So this is a case where we have a piecewise smooth curve. We have C1 and C2. So we're going to have to break this up into two problems. We want the work along curve 1 and then the work along curve 2. All right, now we aren't given these curves parameterized, so the first thing I'm going to need to do is to parameterize these. So for curve 1, which is from A to B, line segment, starting point 1 to -1, direction vector from A to B, 3 minus 1 is 2. 2 minus 2 is 0, and 0 minus minus 1 is 1, so plus t. That's curve 1. If you prefer, you can write it as vector function, 1 plus 2t, 2, -1 plus t. Let me go ahead and do curve 2 while we're thinking of parametric equations. So if I want to go from B to C, x, y, z, point B is 3, 2, 0, and then the vector from B to C, 3 minus 3 is 0, 2 minus 2 is 0, 1 minus 0 is 1, so 0, 0, 1. So I could write that as R, let me call it R2, is 3, 2, t. Okay, I know I'm going to need the derivatives too. Let me just go ahead and compute those. 2, 0, 1, and R2 prime is 0, 0, 1. Okay, so that's just doing the parameterization. How do we find the work once again? The work, which your book will shorthand, is f.dr, which I told you doesn't really have any good meaning there. It means that we're going to take f dot the unit tangent and turn it into a line integral. But because we know those magnitude of r primes are going to divide out, the shorthand is we're going to do f dot r prime dt, where t goes from A to B. So what we need in both of these cases is just f dot r prime, all in terms of t. Okay? All right, so here's our prime. What's my f? F is this. F is x squared, y squared, z squared. But I need it in terms of t. So where do I get this x? I get it from the parameterization. And I get this y from the parameterization as well. And so my f is going to be 1 plus 2t squared, x squared, and then 2 squared and -1 plus t squared. That's f. So the part that I need for my integrand is f dot r prime. So f dot r prime, which is going to be the integrand, we're just taking the dot product of these two. So 2 times 1 plus 2t quantity squared plus 0 times 4 plus 1 times negative 1 plus t squared. And so the work on curve 1, and this is where I will tend to use your book's notation just to shortcut it. The work up across curve 1 is going to be the integral. By the way, I should have put this up here. The way I parameterize this line segment, its t goes from 0 to 1. And it's going to be 2 times 1 plus 2t squared plus negative 1 plus t squared dt. This is going to give you 9. We need to do the same thing for the second part of the curve, curve 2 I called it. So we need r prime, which we have, and we need f. F is, back up here, x squared plus y squared plus z squared. Whoops, x squared, y squared, z squared. And this time we get the x, y, z from not the parameterizations here, but here. So x is 3, so 3 squared is 9. Y is 2, so 2 squared is 4. And z is t, so t squared. We take the dot product here, f dot r prime, and we're going to get t squared. So the work along curve 2 is going to be the integral from 0 to 1. Why 0 to 1? This line segment, I didn't write the t values, but I parameterized in such a way that 0 to 1 will get me b to c. And so f dot r prime is t squared. And so we're going to end up with 1/3. And so now we put these two together, and we get that the total work for this problem is 9 plus 1/3, or 28/3. So the idea in this section, 16.2 part 2, is just the derivation of work. Where does the idea that work is f dot t ds, that it's actually a line integral, where does that come from? And then practicing with the computation showed us that the r prime divides out, and this is the shortcut for computation. This is what we call direct computation. What we're going to be learning in the next few sections is even shortcuts or different approaches than that. Okay, but I call this direct computation. Okay, one more thing, and I want to tie this together with what we did in 16.2 part 1. When we were in 16.2 part 1, we did some line integrals. Let me just kind of squeeze in over here. We did line integrals with respect to arc length. That's what we focused on, but there also were some like that. And I said, don't worry about the meaning for those now, just know how to evaluate them. We did it by putting everything in terms of t. For dx, we put in dx dt. And for dy, we put in dy dt. And what I told you is that these will often occur in pairs. And so on that last page, the part that I skipped, oops, let me talk about right here for a minute. Sorry, I'm kind of squeezing too much in here. So if we had a vector field like this in general for this curve, what would f dot t ds look like? Well, the shortcut is f dot r prime. So if we're going to do that in general to kind of come up with a formula for that, f is p of x and y, q of x and y, and r prime, if r is x and y, then r prime is dx dt dy dt. And so f dot r prime is going to be p of x and y dx dt, q, oops, it's a dot product, plus q of x and y dy dt. And so that means that this integral, the work integral for a general function like this, would end up being the integral from a to b, those are t's limits, that yellow dot product, p of x and y dx dt, plus q of x and y dy dt, times dt. Now that dt, that differential, that acts just like a number would. We treat it like a variable. And so that distributes, and we would get a to b, p of x and y dx plus q of x and y dy. This was that expression that we saw in the end of 16.2 part 1. We didn't do much with it. But I said that often these integrals with respect to x and y occur in pairs over the same curve. And actually I need to change this. It's not a and b anymore because I'm not writing it in terms of t anymore. So we change this back to be written over the curve. And so we did line integrals of this form, but back then I said, oh, they don't have any meaning yet. Don't worry about what the meaning would be. But now what we find is that if we have a line integral of this form, it's the same thing as having it in this form, that it is the work. So when you're asked to compute a line integral in this form, it's the same thing as computing work. And so you can use these two notations interchangeably. So this problem here, you did problems like this in 16.2 part 1. There's no vector field mentioned. You didn't know that you were doing anything to do with work. And the way that we did this was to put in our x, y, and z from our parameterization. And for the dx, we put in dx dt. And the y, we put in dy dt. dz, we went dz dt. Okay? This problem right here is the same as this problem right here. The computations are going to be the same all the way through. It's just the notation is different. So if you're given a problem in differential form, you can instead write it in vector form if you want, and vice versa. Maybe you saw this problem here in vector form and you would rather write it this way. All right. Next time we're going to talk about other methods of computing these.